Hello. Okay, everything should be ready. Can you see the desktop and you hear me? Does everything seem okay? Is everything okay out there? Let's see. Yeah, okay. All right. Thanks. Okay, so it says here see your homework for your fifth assignment, but uh it's not quite up there yet. See it okay. I've got a little bit more to write on it. So I hope it'll be up there this evening, but there's enough that I can show you. Yeah, I have a copy of it on my computer, so I'm gonna show you what the next program assignment is. Okay, so let me show you what assignment 5 give you. It can start talking about it. So if you want, you can start working on it. I think it'll be up there a little later this evening. Okay, so here I have it on my computer here. Now, what it is, it's an extension of language 7. So let me download language 7 and compare what you have to change in language 7. So it's it's not an extension of language 7. In homework assignment 4, you extended language 7. You added features to language 7. In this assignment, you're gonna take language 7 as it is and just change the way it's executed. So so assignment 5 is not adding new features to the language, it's changing the interpreter in a sense. Okay, so let me show you what I mean by that. Okay, here's language 7. Okay, now the way, okay, where is it? Here's the grammar for language 7. Okay, the homework assignment is going to be, the grammar is not going to change. Okay, now the parser for this language is not really a parser for this language. The parser we're using is this thing that parses trees. Okay, so for example, this parser, which builds the abstract syntax tree, doesn't know that if expression has exactly 3 branches. Okay, this parser doesn't know that. Okay, it's perfectly happy to parse an if statement with 4 branches or 2 branches. It won't complain because it's parsing trees, and a tree can have any number of branches. Similarly, that parser doesn't know that a var has 2 branches. The root var should have exactly 2 branches, and the root for set should have exactly 2 branches. This parser, since it's parsing arbitrary trees, it has no way of knowing the specifics of this language. Okay, now where did we take care of that? The fact that there's only supposed to be 2 branches in var was handled as a runtime check. So under language 7, if you look up the evaluator and you look up, for example, evaluate if. Okay, the first thing it checks is there's 3 branches. So here's evaluate if. It makes sure that the tree has 3 branches. See, the grammar says an if expression should have the Boolean branch, the then part, and the else part. So there should be 3 branches. The parser couldn't care less how many branches an if has. It builds the abstract syntax tree with a root if and any number of branches. Okay, that's what the parser builds. And we can see that. Let me just show you that that's exactly what the parser does. Let me run this thing. Let me run. Oh, okay. The jar file's not there, so I have to. Oh, they're not in alphabetical order. Um, okay. So, oh yeah, there it is. Okay. So run the interpreter. And suppose I say something like, if true, return 10, otherwise return 20, otherwise return 30. Okay, well, that doesn't make any sense. Okay, now I get an evaluation exception, but notice down here that the parser built a 4-branch if statement. See, the parser didn't care. The parser built a 4-branch if statement, and then the interpreter got to that if, said, no, there shouldn't be 4 branches, and it said incorrect conditional expression if true 10, 20, 30. Okay. Didn't try to execute it. It just said there's something wrong here. Okay. Similarly, if I did something like if false 10, okay, again, the interpreter, the parser built that 2-branch if statement because the parser doesn't know any better. I did not get a parsing error. Okay. I got a runtime error. On the other hand, if I do something like this, if true, well, for example, if I just do this, if true, now I got a parse error because that's not a tree. So see, I got a parsing error and not a value exception. The parser didn't even try to parse if by itself because that's not a tree. Okay. Similarly, if I do if true A, B, and leave off the closing brace, the parser says parse error, unexpected end of input. It got to if true A, B, and then there wasn't the closing brace. So that's a real parsing error. Okay. I can also get a token error if I do something like this. If @ 1020, @ is not a legitimate token in this language. There's no use of @ in this language. So the tokenizer caught that before the parser. Okay, so the tokenizer noticed that @ doesn't even belong in the language. Okay, right? And let's see, I think I can get a token error by doing something like the following. Let's see, 1x0. Okay, that's not a legitimate number. Okay, that's not a variable name. It's not a number. Oh, no. Oh, the tokenizer tokenized the 1 as a thing by itself. So it didn't give me a tokenizing error because the tokenizer just pulled the 1 off by itself and treated that as a token by itself. Then ABC became a variable name. Okay, so I could, so yeah, so the tokenizer did tokenize that correctly. In a Java tokenizer, that would tokenize as probably an illegitimate variable name. So we have tokenizing errors, parsing errors, and runtime errors. But a lot of what are runtime errors actually should be parsing errors. Okay, that should be a parsing error. Similarly, that should be a parsing error, but we're using a baby parser. So your homework assignment is, well, the homework assignment is not to write a parser. I thought about that, but I decided that is actually, we haven't spent much time talking about parsers. So what you're going to do is you're going to write something called an analyzer. It's something that comes in between the parsing step and the evaluation step. So you're going to write something called an analyzer. Now, the analyzer is going to do 2 things. It's going to find what should be parsing errors, but it's also going to find errors that aren't really parsing errors either. I'll show you what I mean in a second. Okay, so your job is to write something that sits between the parser. Okay. See, parse tree takes what the tokenizer runs first, and what comes out of the tokenizer is fed into the parser, and then what's comes out of the parse tree goes to the evaluator. So you go tokenize, parse, evaluate. Okay, that's standard for all interpreters. They all work that way. But our parser is really a bare bones parser. So what we're going to do is in between the parse and the evaluate, we're going to put something called analyze. Okay, so in the homework assignment, this is going to be the code you'll get for the homework assignment. Okay, there'll be the tokenizer, and what comes out of the tokenizer will go to the parser. It's still the same parser. It's going to be this baby parser that doesn't really pay much attention to. It just parses trees. Doesn't really know anything about the language, just parses tree. But then what comes out of the parser is going to go to analysis stage. The analysis stage is going to analyze the parse tree and reject things that aren't right. Okay, and it's going to find 2 kinds of errors. is going to find things that should have been parsing errors, and then it's going to find errors that could never be parsing errors, but are errors that you don't want the evaluator to find. Okay, and I'll show you what I mean by those in a minute. They're called static errors. So this all compilers have this step here. In fact, in a real compiler, you don't go from tokenizer to parser to evaluator. You go from tokenizer to parser to analyzer. There's always an analysis step after the parsing step. Even if you have a sophisticated parser, there are errors that the parser cannot find. Okay, but that you don't want the compiler to find. There are errors that can be found between parsing and interpreting or compiling. So I'm going to show you a few of those in a minute. So you have to find two kinds of errors when you write the static analyzer. You have to find what should be the parsing errors, and then some more sophisticated ones. Okay. Now, here's what we're going to do. If you look at the evaluator in this case, this is language 7's evaluator, and then you look at the evaluator you're going to get with this one. You're not going to touch the evaluator. In the assignment 5, in assignment 5, you're only going to write that one code. All your work is going to be in that one file. All the other files here, you're not going to have to touch. So you're going to do all your work in the static analysis file. Okay. So what I did is I stripped out of the evaluator. Okay, here's the original language 7 evaluator. Here's the new one. Okay. If you go through here, you'll see a whole lot of lines of code says runtime check. Okay, so here I'll search for them. Okay, there's a whole bunch of runtime checks. They're everywhere through this code. Runtime check, runtime check, runtime check, runtime check. Many of those runtime checks should have been caught by the parser. Okay, many of them should have been caught by the parser. So the first thing you're going to do in your static analyzer is now what I did is I took all those out of this one. They're no longer in here. The runtime checks that should, like this one. Well, let's go back up here. Look at evaluate if. Okay, see, evaluate if starts with checking for 3 branches. If you go to the homework assignment, you go look at evaluate if, it doesn't bother to make that check anymore, because as soon as that check has been done by the static analyzer or the parser, it could have been done by a parser. See, here now, evaluate if does not check for 3 branches. Okay? It assumes that there are exactly 3 branches there. Here, because we had a lousy parser, the evaluator needs to check for 3 branches. Okay, that test is no longer in the evaluator. It's going to be gone from the evaluator. You're going to move this test into the analyzer. Okay, so I'm going to give you a bare bones analyzer. The analyzer, when you get the homework assignment, the analyzer will have a little bit of code in it, but you're going to have to add a lot of code to this. So you'll have to essentially copy this code. Some of it's going to be real simple. You'll just copy code from the language 7 evaluator into the homework 5 analyzer. And this thing will change from evaluate if, in the analyzer will be called an analyze if. The evaluator, this one analyzes things, not evaluates them. So this will become analyze if. Then there'll be a method analyze while. And then notice that while, first thing it does is check for 2 branches. A while statement should have 2 branches, the Boolean part and the body of the while loop. Okay. In the new evaluator, there is no check for 2 branches in evaluate while. That check for 2 branches will move from evaluate into the analyze program. Okay, so analyze while will start off with this. Okay, and then we'll see what else it might do, but it'll start off with this. Okay, it'll catch things that could have been caught by the parser, but it'll be caught by the analyzer. Okay, so a lot of the runtime checks in the evaluator will turn into analysis checks in the static analysis. Now, it's going to be a little bit tricky. Some of the runtime checks in here are really parsing errors. Some of the runtime checks in here are deeper than that. They're not parsing errors. Okay, and some of the runtime. Okay, uh, some of the runtime checks in here could have been done by a parser. Some of the runtime checks can't be done by a parser, but they can be done by an analyzer. And some of the runtime checks have to wait till runtime. Some of the runtime checks really have to be runtime checks. So this one should really be a parser error, but we don't have a good parser. So instead of being a parser check, it's going to turn into an analysis check. Okay, so this one will turn from a runtime check to an analysis check. Okay, but there are some things in here that are runtime checks that actually have to stay runtime checks. Okay, and I'll show you in a minute what I mean. So the runtime checks in here fall into three categories: things that could have been parser checks, things that could have been done by the parser, but we're going to still have them done by the analyzer, things that can be done by the analyzer, and then things that have to be left in the evaluate. Okay. Now, the things that have to stay in the evaluator are the type checks. That's the things. See, here's the evaluator that you're going to get in homework 5. The things that it has, the runtime checks that it still has, turn out to all be type checks. Runtime type check, checking that something has the right tag. Okay, so if you see well, there's one this is the only one that's not a type check. Type check, type check, type check, type check. See, all the others are type checks. Okay, there's only one runtime check left that isn't a type check. Now I'll tell you in a minute what that is. But if you go through here, oops, I just passed it. There's only one runtime check left in the new evaluator that wasn't really a type check. It's something that can't be checked by the parser. It can't be checked by the analyzer. It has to be checked by the runtime. And we'll show you in a minute what that is. Besides the type checks, okay? The type checks, now the type checks are there even in the Python interpreter. So for example, the Python interpreter also has all these runtime type checks. They're in Python's runtime interpreter. Same with JavaScript. JavaScript also has to do all these runtime type checks. That's because they're untyped languages. So they pay a penalty. They cannot check types at compile time or analysis time. Okay, so type checks, because our language doesn't have types in it, we don't say int variable. We don't declare the type of a variable. So like JavaScript and like Python, we cannot get rid of the runtime type checks. Okay, we'll see how that works. Okay, so there's the real low-hanging fruit, the things that should have been easy parser checks, but our parser is so simplistic, we're going to move these easy parser checks into the analyzer. It actually turns out to be easier that way. Making these parser errors actually is not that easy. Parsers are hard to write. And I think a fair number of languages actually play this game. Instead of making the parser really sophisticated, I think a lot of languages actually do punt and leave things up to the analyzer instead of doing them in the parser, because parsers are hard to write. Okay, so in a sense, it's almost more efficient just to keep the parser simple and leave the analyzer to find some of what should have been parsing errors. Okay, in our case, we're going to throw a lot of the parsing errors into the analyzer. Okay, right now, what can the analyzer check that the parser can't check? That's the next step. What is it that the analyzer could check that the parser can't? Okay, now let me run it. Let me go back to the program and give you an example. Suppose I set x to 4. Well, there is no x variable, so I'm going to get an evaluator exception, undefined variable x. Well, it turns out that error could be found before you run the program. Okay. it's possible to, and this is what I'm going to talk about, it's possible for the analyzer to analyze a program and find out what variables have been declared and which variables haven't been declared. So that could be caught at before runtime. That could be an analysis error, not an evaluation error. And that matters because suppose you write 1,000 lines of code and somewhere in there you accidentally have a misspelled variable. You hate for the program to run for an hour and then hit the undeclared misspelled variable and then blow up the program. Why not know before you run the program that you have an undeclared variable somewhere, that you're using a variable that's undeclared? Okay, so if you can find an undeclared variable before you run the program, it's a lot better. Now, Python and JavaScript can do this for you. They can find variables. Well, actually, that's not quite true. Because of the way JavaScript works, it's got a problem. It can find it. In JavaScript, the way the language works is that if you set a variable that hasn't been declared, that actually declares the variable. They actually define the language in a very dumb way. And by definition, if you set a variable that's never been declared, that creates the variable. So if you have a variable, a legitimate variable called I'm trying to think of a good example. Like you have an array called student, and then at some point later on, you have an array called student, and then some point later on, you think, oh, my array was called students. Student array, students array. Well, suppose it was declared student, but at some point you accidentally think of it was called students. In JavaScript, that just creates a new array called students, and your program continues running. Now you have two arrays, one called student, one called students. That's really bad. Your program is now running in a way that you never intended it to. But that's actually what JavaScript does. By definition, if you set a variable that has never been declared, it just creates the variable on the fly. That's really bad. Okay, now if you put Java in strict mode, JavaScript, if you put JavaScript in strict mode, then it doesn't work that way. In strict mode, if you have a variable called student and then you accidentally set students in strict mode, it just tells you that there's an error there. It tells you when it analyzes the program, it analyzes it, sees that students was never declared, and instead of creating it on the fly, it reports a static error. Before it runs the program, it tells you, oh, you have an undeclared variable here. But you have to put the JavaScript language in the strict mode. This is one of the big problems. You have to put JavaScript in strict mode, and then it finds these errors that it wasn't designed to find. And everybody in JavaScript knows to have all their programs use strict mode because the language is designed in a broken way. Why don't they just fix the language? Same old story. Once a language has been set in stone, you can't ever really fix it. Because then you'll break old code. So instead of fixing the language, they kludge onto it a strict mode. And then they just tell people use strict mode as opposed to sloppy mode, which is what the default is sometimes referred to as sloppy mode. That's the language, that's real. Sloppy mode is JavaScript. Okay. So in the JavaScript language, something like analyzing a program for an undeclared variable. So for example, if I set X to Y, I have two undeclared variables there. X has never been declared, Y has never been declared. Now my runtime program finds the X first and says undefined variable X, because it was trying to set X and see it finds it and says no. Now notice that the Y was undefined too. Your analyzer will report two errors on this line. When we get to the analyzer, actually here, let me run the analyzer. Here's the analyzer. See, now this is language 7 with an analyzer. If I say set X, Y, I'm going to get two error messages. I get an analysis error, undefined variable X, undefined variable Y. Okay, so I get two errors. Notice that I've also added line numbers and position numbers into the error messages here. I was actually going to go back and put that in language 7 too, but it starts becoming real important. For example, here, set X to be X. There's two errors there. Notice that that's X at line 1, position 6. That's this X. X at line 1, position 8. That's this X. So you kind of need to know which variable. So you like once we get to real precise error messages like this, we need to know what line it's on and what position it's at. So I added those to the error messages. They're actually there. I forgot to use them in this language. The tokenizer, the tokens carry with them their line number and their position number. That's been there all along. I wrote the tokenizer so that every token knows where it was defined, what line it was defined in, and what position it was defined at. But then I actually forgot to use that information in some of the interpreters. I forgot to use that. So in language 7, it just get undefined variable X. And it forgot to say at line 1, position, blah, blah, blah. But for this homework assignment, it's real important because otherwise you'll just see undefined variable X, undefined variable X. And it doesn't make any sense. But it's two different X's. Both of them are undeclared. Okay. Now on your hand, if I do this, var X, X, I'm declaring that X. So it doesn't need to be defined. But I can't declare a variable in terms of itself. This X should be already defined. This should be an X in an outer scope. So this would make sense if I have an X in an outer scope and I'm declaring a local X that's a copy of the outer X. Okay. But here, the error message would be undefined variable X at line 1, position 8. So it's this X it's complaining about, not that X. See, it's important which X is being analyzed here. Okay. Notice that this declared X, it put it in the global environment. You know, it's saying you're declaring an X, but you goofed up what it's initialized to. So it notices that there should be an X. So for example, if I did this, begin block, var X, X, set X6, there's nothing wrong with this X because it's that X. But this X got goofed up. So I'll get an error message about that X, and I won't get an error message about that X. See, I only get one error message. That X is the bad one. Nothing wrong with that one because I'm declaring it. I goofed up what it's initialized to, but it does exist. So this X is okay. It's really referring to that X. Okay, so only one error message. So out of 3 X's, I need to know which one it's now 15, you can count from the beginning and you'll see that that's that X. Okay. So your analyzer is going to, it's kind of, it's starting to get close to how a real compiler works. The analyzers analyzes this pretty well, and it'll say, well, that X is being declared, so that's okay. But that X should have been out from an outer scope, and there is no X in an outer scope, so that X doesn't exist. That's the offending X. Then this X is that one. So there is an X to set here. It's that X there. Even though it wasn't initialized properly, it's still declared properly. So this one's okay. All right. So you only get one analysis error. Now this is debugging information here. You can turn off the debugging information if you want. So you can run this program with or without the debugging information. Like right now, it's running with the debugging. So you're seeing that the analyzer had to build an environment to store that X in so they could tell that there is an X for this guy to refer to. So the analyzer mimics some of what the interpreter does. The analyzer builds environments to store variables in so it can keep track of what's been declared and what hasn't been declared. But the analyzer does not run your program. So for example, if I do something like here, watch. While true, print X. Okay, now that's an infinite loop. If my program was running, well, actually, now if I do that, my program will run forever. There's nothing wrong with that. While true, print 0. Okay, actually, go ahead. See, runs forever. Okay. Okay. So now so that was an infinite loop. Let me start the interpreter back up again. Okay. While true, print X. Now, you don't want to start running this while loop. You don't want to run the while loop. You just want to analyze it and say there's an undeclared variable in it. Okay. So the analyzer is not supposed to execute that while loop. It just steps through it, analyzes it, and then goes on. Okay. The analyzer doesn't actually do the whiling. Okay. So the analyzer isn't supposed to mimic what a program does. It's supposed to just step through the abstract syntax tree looking for errors. So the analyzer just looks at the abstract syntax tree of that guy. See, let me clean this up. Run that again. Okay. Now, there's the abstract syntax tree. The analyzer looks at this abstract syntax tree, and it notices that at this point, there is no variable declaration, so the environment is empty, so there's no X in the environment. So the analyzer will create an environment. It won't have any variables in the environment. When it sees X, it'll complain. Okay. So the analyzer is not going to loop on this while loop. That's not the analyzer's job. It'll just check this branch to make sure it looks okay, check that branch to make sure it looks okay. When it gets here, it'll say, oh, something's wrong. There's an X that doesn't belong there, and it'll complain. Okay, but it won't try to execute the while loop. The analyzer will not do function calls. It will not do Boolean expressions like if, another example is if true while true print 0. X. Okay. Okay. If you were executing this, this is an interesting one. The interpreter will never see that X because the interpreter goes, if true, okay, true, go to the while branch, while true, print. The interpreter will never see that incorrect variable. So if I take this one here and I put it over here in the interpreter, well, I'll do it over here in the interpreter. I'll say if true while true print 0 X. Big infinite loop. Never got to the X. Okay. Now the analyzer will walk that tree and it won't try to do the while loop. The analyzer will walk that tree and see, oh, there's an X here that's never been declared. And it'll never get passed to the interpreter because if there's an analysis error, you don't give it to the interpreter. Just like a compiler doesn't try to run, if your program didn't compile, there's nothing to run. If your program doesn't pass the analysis stage, there should be nothing to run. So even though there's an abstract syntax tree, the abstract syntax tree now has this error in it there. Again, if you just interpreted this, you'd never get to there, and you'd never know you added a variable that was poorly declared. This is a really good example of the difference between what an interpreter does, like catching errors at runtime, what it means to catch errors at runtime versus to catch errors at parse time or analysis time. The analyzer looks at the whole abstract syntax tree. The evaluator doesn't. The evaluator only looks at what it has to look at. So if true, it only looks at that part of the tree, and that part of the tree happened to be an infinite loop. So it never needed to look at that part of the tree. Okay. In fact, let me go back and run this again. Do the following. If true 0 else X. Runs. See? Notice that the interpreter didn't actually look at the X because it was if true. True is true, so it only looked at the left branch and it returned the value 0. If true 1001, see, it returned 1001. It didn't even notice that there was a bad variable there. JavaScript in non-strict mode would work just like this. If the interpreter didn't walk to that guy, it wouldn't even know it was wrong, anything wrong with it. Okay, if the interpreter didn't walk over there, the interpreter won't see any error there. The evaluator walks the whole tree, and if it finds anything wrong in the whole, it evaluates the whole, it doesn't execute the whole tree, it evaluates the whole tree. The evaluator, since it's evaluating the tree, it only evaluates the parts that it needs to. So the evaluator only evaluates what it needs to. The analyzer analyzes the whole tree. Okay, so there's a big difference there. Okay. All right. Now, these kinds of errors, like undeclared variables, cannot be found by a parser. And this is important. An error like this, okay, there's two undeclared variables in there. The reason the parser can't find them is because this, like, look at that statement. Okay. Now look at this statement. Okay. Notice that this part here, that part there is syntactically exactly like this. From the point of view of the parser, this and this are exactly the same. If there's nothing wrong with this, there's nothing wrong with this from the parser's point of view, because we're parsing what are called context-free languages. Okay, so our parsers, we didn't spend a whole lot of time at the beginning of the semester talking about parsers, but our parsers are all what are called context-free grammars or languages. Okay, context-free grammars or context-free languages. That means that if something is correct in one context, it's free in any other context. Notice in this context, there's local variables. In this context, there isn't. That cannot be detected by a context-free grammar, because the context-free grammar says either that's grammatically correct or it's not. It is okay in this setting. It's not okay in that setting. That means it's not a parser error. It's a analysis error. Okay, so this one will analyze properly. See, it executed. See, there was no analysis error there. Okay, it put X in the environment, it put Y in the environment, then it did the if expression and gave me back the proper value. It gave me back X. This thing executed. Okay, it passed the analysis stage and executed. So there's nothing wrong with that piece of syntax there. There's nothing wrong with that piece of syntax. But over here, the parser would never notice that there's anything wrong with that. The parser would just build a parse tree that was a legitimate parse tree. But the analyzer can say, oh, there's no X. Okay, so anything that would be correct in one context, but incorrect in another context is not a parsing error, because the grammars are all context-free grammars. That's all programming languages use context-free grammars. So that means that so every compiler, when it tells you have an undeclared variable, that's never the parser that found that. When a compiler tells you have an undeclared variable, it's always the analyzer stage of the compiler that finds those. Undeclared variables can only be defined by an analysis stage, never by a parsing stage. Okay, now what the parser can figure out is that if true X, Y, Z, okay, 4 branches on an if don't make sense. The parser, that's never correct. There's no context in which if can have 4 branches. So that can be a legitimate parser error. Now, in our case, it's a val exception, but it could have been a legitimate parser exception. Okay, because there's no context in which that's correct. Okay, right. So your analyzer will, in addition to finding the obvious parsing errors, which you're going to copy all of them from the previous evaluator into the new analyzer. So you can go in here. This evaluator, it's got all these runtime checks. Many of them you'll just copy and paste them from the language 7 evaluator into your analyzer for your homework assignment. So you have to figure out where to put them. And many of them will just copy whole, actually, you'll have to, the analyzer doesn't throw, oh, here's another important difference. The analyzer doesn't throw exceptions. That's so it can find more than one error. So again, if I do this, there, X, Y, notice I want, that's a bad example. There, Bob, Alice. Oh, I'm sorry. Set, apple, orange. 2 errors. Now, if I was throwing exceptions, as soon as I throw an exception, I can't find the second error. So the analyzer does not throw exceptions. The analyzer is going to be a Boolean function that returns true or false. If this thing doesn't analyze correctly, it returns false and you report an error message, but then you continue analyzing. The analyzer wants to be kind of like a compiler. Just because you found one error doesn't mean you give up. You keep looking for more errors. Okay, so you report as many errors as you can. Unlike an evaluator, the evaluator has to quit as soon as it finds an error. So when the evaluator says set apple to orange, there's really not much it can do. Once it finds out that apple doesn't make sense, why even bother to go evaluate orange or whatever? Their evaluators usually can never make progress after they found one error. The evaluating just doesn't make sense. You're trying to do things in the evaluator. The analyzer, just like a compiler, if it finds an error, why not just report all the possible errors it can find? Just like a compiler, sometimes the errors that come afterwards are bogus errors. And your analyzer will actually report some things that probably shouldn't, that aren't really errors, just like compilers do. Sometimes when they see one error, sometimes it means that the other errors aren't really errors. Okay, so like here, something like one of those is an error, but who knows which one really is? I probably, this is probably a case of misspelling something. Okay, now one of those is, now in this case, the interpreter will treat this one as correct and this one as incorrect. And the analyzer will treat this one as correct and this one as incorrect. So this is not a case of 2 errors. So now let's see. And let's see if I can get an example where it's reporting 2 errors when it really shouldn't. Oh, what would be a good example? Oh, I can't think of one offhand. But you see that all the time. You're taught that when you get a bunch of compiler errors, you only fix the first one, because the other compiler errors may actually just depend on the first one. Okay, so you tend to always fix one compiler error at a time, and because one compiler error can just generate one mistake can generate dozens of compiler error messages. So you only really pay attention to the first one. Here, the analyzer is a little bit like that. Sometimes the first error reported will actually be the only one that really matters. The other ones may just be not really they're not really errors. If you fix the first one, the other ones will go away. Okay, but that's not always the case. In this case here, apple and orange are both undefined. So there really are 2 errors there. Okay, it isn't like the second error somehow would be fixed if I only fixed the first error. Okay, then you can come up with a little bit of thought. You can come up with examples where the second error fixes itself if you fix the first error. Offhand, I can't think of a good one like that, but I should be able to come up with something where if I fix the first error, that automatically fixes the second error. So there really was only one error. Okay, so the analyzer is a little bit like a compiler. It's going to keep on reporting errors. It's not going to throw exceptions like the evaluator does. The evaluator quits. As soon as it finds one error, it stops. The analyzer keeps on going. Okay, now your analyzer has to find undeclared variables. Oh, here's another thing it should find. You can't declare a variable 2 times. So local variable already exists. X at line 1, position 23. That X is being redeclared. So you're not allowed to redeclare a variable. Okay. So you can't declare a variable 2 times. That's standard in Java and C and C++. You can't declare a variable 2 times. So you should find undeclared variables. Okay. So if I set Y, that's an undeclared variable. Okay. So find undefined variables, find duplicately declared variables. So if you redeclare a variable, you can find that. If you use a variable that hasn't been declared, you can find that. That's 2 kinds of runtime, 2 kinds of analysis errors you can find. Oh, these will be detailed in the HTML page for the assignment. I explained to you in there, which I'm just showing you here, but I explained it in the HTML page. Here's another example of something you can catch. If I declare a function, f lambda, here's a function of 2 variables that returns the product of the 2 variables. Okay, so that's a legitimate declaration. Okay, so f is the function that takes in x and y and takes their product of x and y. But I could goof up and do that. Okay, I can't redeclare a parameter. See, oh, that was missing 1 parenthesis. So notice that was a true parser error. I forgot one of the closing parentheses. So that was a true parsing error. That thing did not build a legitimate tree. Okay. Notice I got repeated formal parameter x at line 1, position 18. So that x, okay. And then also since I repeated the x, there was no y declared. So I got, see, now here's an example where the second error really goes away if I fix the first error. Okay, I really meant that to be parameters x, y, x times y. So I hit upon the example I wanted a minute ago. To fix the solution here was that was supposed to be x times y, and then that fixes everything. Okay, so the analyzer is supposed to, when the analyzer finds a mistake, it doesn't stop with that mistake. It keeps on analyzing. So it finds this x and says, well, that's a copy of that x. You can't have a variable declared 2 times. Then it goes in here and says, well, that x is those guys, but that y is undeclared. And it doesn't know that it was supposed to have been that x. So it tells you that there's an undeclared variable. So you get 2 errors, repeated formal parameter and undefined variable. Okay. And it tells you exactly where they are. See, line 1, position 25. So this guy's undeclared and this guy's repeated. But if you fix this one, you'll also fix that one there. Okay. So you can find in function definitions undeclared variables. You can find in function definitions repeated parameters. Okay. Notice that that's a context error, because if I go over here and say begin there y4, then go here fun f lambda x times xy, that's not an undeclared variable now. Oh, see, yeah. Well, actually, no. See, that y is it, yeah, that y is a mistake here, but it's not a mistake here, even though it's the same syntax. I need to close let's see. So I need, see, that closes the multiplication, that closes the lambda, that closes the fun, that closes the begin. Okay. This piece of syntax looks exactly like that piece of syntax. This y is okay because it's actually that y. So that means that this is a context error, not a context-free error. So it's not a parser error. It's, yeah, the fact that this y is undeclared, again, it's not a parser, could never figure that out. because in this context, the y is an error. See, undefined variable y. But in this case, I only have one mistake. I have the repeated x. There's nothing wrong with that y because I declared a y here. And you can see here that there was a see the debugging information shows you that the analyzer had to build an environment to test this thing in. So it built an environment holding the f, and it built an environment holding the y so they could test this thing. So the evaluator does a fair amount of the work of an interpreter. This is why this is a great homework assignment. You have to actually have a pretty good sense of what the interpreter is doing, because the analyzer needs to mimic a lot of what the interpreter does. The analyzer needs to build environments so they can put variables in the environments to check if the variables have been declared or not. It doesn't run any of the code, but it does build the environments. Okay, and this is explained a little bit more detail in the help page that goes with the homework assignment. Okay, but so it's a real good test of your understanding of the evaluator. So the analyzer is kind of a stripped down evaluator. It does some things the evaluator does and a little bit more, and it does things a little bit less than what the evaluator does. Like it doesn't do while loops, okay, but it does build environments. And unlike the evaluator, whereas the evaluator halts whenever it finds something wrong, the analyzer will keep on analyzing. Okay, so unlike the evaluator, which just throws an exception when it detects an error, the analyzer keeps on trying to analyze. Okay, so even though it found that error there, it went ahead and analyzed this thing in here. Okay, now it didn't find an error in this one, but over here, it found that error, and then it said, oh, there's an error here too. In this case, in this one here, it found that error, and then it checked in here and didn't see anything wrong, because that x is the parameter and that y is the local variable. So there was nothing wrong with that, but it did check those. Okay. Now if I go here and make this the variable y2, now there's two errors. There's a repeated parameter and an illegal. Let's see. Illegal expression. Did I do something wrong? Let's see. What did I type? I shouldn't have got illegal expression. I should have got undeclared variable. Huh. I don't know what happened to that too. See, it didn't show up here in the Lambda. I think maybe I typed something wrong. Oh, I know it's wrong. I've already declared f, so it's telling me that I'm redeclaring f. You can't declare a function more than once. So I think I'm getting a problem. No, that was. Oh, stupid me. Language 7 doesn't allow local functions. Yeah, actually, I'm getting an error because language 7 doesn't allow local functions. So I can't define functions inside a begin block. So this is a really bad example. I wasn't paying attention. That's language 8. So this was code in language 8, not language 7. Language 7 lets you define, so I should have made this prog. Instead of being, I should have been paying attention. This should be prog. Now I have a program with a local variable and a function. Okay. Now what did I do wrong? Oh, and prog doesn't work inside the interpreter. Yeah, I wrote the REPL. The REPL does not understand prog. Yeah, so I actually can't do this example in the REPL. I can't do this example in the REPL because I can do it by breaking it up into two steps. I have to do var y4. That puts y in, and then I have to say fun f lambda x times x, y2. Well, if I do y, okay, repeated formal parameter. Okay, see, I only got one error. No. Then I got this error message that I already have an f. See, I already have an f. So yeah, I can't use the name f again unless I just stop the interpreter and start over again. Yeah, once I've declared one f, I can't use it for examples anymore. You can only have one function with of that name. So I can't keep using f for my name in my example because I already have an f. So I would need to make this like g here, g2, say. Oh, that was okay. Okay, now I get what I wanted. Well, this one had the repeated formal parameter missing. Okay. Then if I do G3 and make this Y2, now I'll get two errors. Repeated formal parameter, undeclared variable. Notice I have to keep bumping up the function name because once I have an F and a G, I have to create new function names. Okay, so you got to be careful in the REPL. You have to be a little bit careful. Okay, so in the REPL, you have to obey all the rules of the REPL. The REPL doesn't let you use prog. You can't use prog in the REPL because the REPL is not evaluating programs; it's evaluating expressions. Same thing is true in JavaScript and in Python. The REPL doesn't evaluate programs; it evaluates expressions. Okay, and the other thing is I'm doing language 7, not language 8. So you can't put functions inside of begin blocks. There's no nested functions in language 7. Okay. Okay. Now let's see what else. Okay. So far you have to find undeclared variables, redeclared variables, repeated parameters. Repeated parameters. You have to check the body of a function to make sure that all the variables in the body of a function are declared. Okay, so it's not just at the top level. You have to find functions. You have to find mistakes in declarations of in the body of a function also. So if a function uses a variable that isn't declared globally or as a parameter, that's an error. The variables in the body of a function, since there's no nested functions, every variable in the body of a function is either a parameter or a global variable. Okay, so you have to check for that. Okay. Now here's another thing you have to check for. Let me clean this up. Let me just quit and start over again. Here's a function f that takes two variables and just takes their sum. Okay. Now here I'm going to apply the function to. Now let me do that over here. Now here is the language 7. Okay. So in language 7, I'm going to say fun f is lambda x, y, the sum of x and y. Okay. Now apply f to 1, 2, 3. That's too many parameters. Okay. Now, as at runtime, it figured out that there were too many parameters there. Okay. But it actually did that at runtime. Over here, you can figure that out at analysis time. Okay. Right. Now, there's a little bit of subtlety going on here. Of course, at runtime, you can look up f and you can see how many parameters f needed in its definition. So when you apply f, you look it up and you see it took 2 parameters and you see there's 3 arguments here. So you can say, well, the number of arguments here and the number of parameters here don't agree. You get a runtime error. Okay. Over here in the analysis stage, it's kind of the same thing. You analyze this apply, you look up f in the environment and you see how many parameters it takes. And then you look at how many arguments there are here and you can match them up. But there's something a little bit tricky over here. Suppose I declare a variable G, which is just another name for F. I can do this all I want. I can create, this is my functions are first class. So G is just another name for F. And I can do that over here too. I can say var G is another name for F. Okay. Now apply G to 1, 2, 3. Okay. You look up G, okay, and you find out that it's got the wrong number of arguments. Okay. But over here, things are a little bit subtle. If I apply G to 1, 2, 3, I did not get an analysis error. I got a runtime error. The analyzer can only analyze globally defined functions like F, not G. G is a name for something that's a function. G actually isn't really the function. See, this thing made G a name for the function, but it's not actually really the function itself. That makes a difference in the analyzer. The analyzer can only analyze the globally defined functions, okay, not variables that point to functions. Okay, so the analyzer didn't catch that error, the evaluator did. Okay, you can see the analyzer caught the problem with F, but it doesn't catch the problem with G. It leaves the problem with G up to the evaluator. That's because G's not really the function. G was just an alias for the function. Okay, so in your analyzer, there's a little bit of tricky code where the analyzer, when you have a function call, the analyzer has to look and say, oh, is this name the original name of the function, or is it a renamed version of the function? Okay, and it has to check that. If it's the original name for the function, it's the name that's stored in the global environment, then it can analyze it. It looks in the global environment and checks how many parameters are. If the G is really just a variable, it can't go, see, because it doesn't know how many, like here's what I can do. Var H is G, var K is H, var J is K. Now apply J. Now really what happens there is, well, J is K and K is H and H is G and G is F. But there's no way the evaluator can figure out all those chains. You can kind of see, notice that this thing is not really legitimate here. J is really K, K is really H is really G, and G is really F. Even though, see here, it's kind of obscuring the fact that G isn't really F, G is pointing to F. And H is pointing to G, which points to F. And K is pointing to H, which points to G, which points to F. And the analyzer cannot keep track of all this. It would just be impossible for the analyzer to keep track of all this. So the analyzer can only analyze F. See, F, but if it analyzes any of the other ones, it just punts and it leaves it up to the evaluator to figure it out. The evaluator will evaluate G to get K, evaluate K to get H, evaluate H to get G, evaluate G to get F, look up the parameters in F and find out they don't match the arguments here. The evaluator does all that work. The analyzer, it actually, you can show that the analyzer can't do all that work. If I create this program a little bit more complicated way, I can make it so that there's no way in the world the analyzer can keep track of what's going on, because the analyzer is not supposed to run the program. Because I could have like an if statement. I could do something crazy like if some condition set G to F or set G to H. So the value of G might depend on the condition that was here. So if G is a function, G is either F or it's H, how in the world is the evaluator, the analyzer, supposed to know when you call G what it's calling? See, this thing can't be, this is an example of what the analyzer cannot sort through. G could be a name for F or G could be a name for H. F might take 2 parameters, and H might take 3 parameters. But G could be a name for either one of them. So if later on I call G, the analyzer has no way of knowing what the right number of arguments for G is. Here's a tough question. How does Java figure this out? Because you can do this in Java. An interesting question is, how does Java keep track of this stuff at the analysis stage? See, Java can figure this out at the analysis stage. It doesn't need to run the program. The answer is Java gives a type to each of these variables. If F has type 1 input, then G has to be a function of 1 input. If H has type 2 inputs, G cannot be a name for both H and F. This would give you a compiler error. If F takes 1 input and H takes 2 inputs, then you can't have G be a name for either of them, because then G would have an inconsistent type. So the compiler keeps track of the types of everything. The compiler would not compile this line. It would say F is a function of 1 variable, H is a function of 2 variables. You can't have G be a name for either of them. G can only be a name for one of them, because G has to have a type of either a function of 1 variable or a function of 2 variables. So this would not compile. The compiler would see that there's, the compiler keeps every variable has a type. So function names have the type that keeps track of how many parameters they take. A function's a function of 1 variable, a function of 2 variables, and it keeps track of the type too. So a function can be a function of 1 int, or a function can be a function of 1 double. Those are not the same type. A function can be a function of 2 strings, or a function could be a function of 2 ints. Those are not the same type. So the compilers keep track of the types of these function names, and then it can do the analysis. It can do the analysis. In our case, we can do JavaScript like things like this. See, JavaScript has a terrible time with this also. G can be a name for F, or G can be a name for H, and F and H don't have to be the same kind of function. So JavaScript has the same problem our language has. JavaScript does not know what G really is, what kind of function G is. So when you get down later on and you say apply G, the analyzer has no idea how many parameters G really takes, because G could be a name for F or it could be a name for H. So this has to be checked at runtime, not at analyze time. This is a limitation of even the Python analyzer and the JavaScript analyzer. They cannot analyze function calls very well. They can only analyze the function calls to the globally defined functions directly. If you call that function directly, the globally defined function, then it can analyze it. But if you're calling a function by name and the name is a local variable, it cannot track down what real function that thing is a name for. It can't track it down. It has to run the program to find out what G is really a name for, because there could be these indirections like this if statement. To know what this if statement did, you have to know what this condition is. To know what that condition is, you might have to track down a whole bunch. You have to essentially run the program. To know whether G is a name for F or G is a name for H, you essentially have to run the whole program. Okay, so you cannot do it in an analysis stage. So your analyzer will analyze the applications of globally defined functions, but it won't analyze the applications of variables that are local variable names. If this is a local variable name, not the name of a global function, then the analyzer skips over the analysis of this. But if this is the name of a globally defined function, then notice that the analyzer here, see how that's a lambda, these aren't. That's a little bit of a clue that see the analysis environment and the global environment look different here. This is the analysis environment. This is the global environment. The global environment actually makes it look like these are all functions, but in fact, they're not really. G is K is H is G, and G is F. Okay, so there really is a difference between these and this guy here, even though it looks like they're all the same. Okay, all right. So your analyzer will analyze globally named functions. It won't analyze variables that name functions. Okay, so there's some tricky code in the analyzer. The analyzer has to make some interesting distinctions. And in the help page for this assignment, I'll give you a little bit of some information about thinking about these things. Okay, so it isn't finished yet. There's the HTML page. See, here's an example of something of what the analyzer can handle and it can't handle. See here, there's two globally defined functions, but then there's some local variables of the same name. So f points to g. So this local variable f is going to point to that function g, and this local variable g is going to point to that function f. And down here, analyzer cannot do this. See, so this is an example. The analyzer cannot sort that out. It cannot sort that out. And the analyzer has to keep track of, well, this is not that variable, it's that local variable. Since that's a local variable, it does not analyze that application. Same here. That is not that global variable, that's this local variable, so you don't analyze that application. Okay. The environment object has methods in it that let you ask, is a variable defined locally or globally? So we go to homework 5 in the environment class, there's a method for determining if a variable is defined globally or locally. You can tell if a variable is defined globally or locally. There is a defined local method. They'll tell you a variable is defined in the most local environment. But what if it's defined between the local environment and the global environment? So it's not local, but it's not global. So then there's a separate method for that, define global. If a variable is not defined local and it's not defined global, it's defined somewhere in between. So there's three possibilities. A variable is in the local block, like if you go up here, it's in this local block, or it's in a block between the global block and the local block. So if there could be a begin in between here. So the variable can be defined globally, locally, or in between. Okay. Defined global tells you when it's defined globally. Defined local tells you when it's defined at the lowest, at the the innermost level. That would be, this one says defined local. Where is it? I lost it now. Okay. If it's not defined local, it's not defined global, it's defined somewhere in between. Okay. So you can figure out the three cases. What's defined locally, what's defined globally, and if they're both false, it's defined in between. But usually you don't care about that. You just need to know, is it a local definition or a global definition? So your evaluator, your analyzer will make use of these method calls in the environment class and ask questions about, is this variable local or is this variable global? So here, it'll ask when it wants to check this, it wants to know, is that a local variable? If it is, don't analyze the apply. If G is global, meaning it's really that G, then you analyze it. Okay. All right. Now, one last thing. I have a bunch of test cases in the homework assignment. Okay. So when you download the homework assignment, there's two files here. This guy analyzes the simple errors that could have been found by a parser. So I kind of separated them to make it a little bit easier for you. Do these first. These are the simpler things to check. They could have been found by the parser. All of these, the code for them is actually in the current evaluator. Every one of these is checked for by something in the language 7 evaluator, and you basically have to move it from the language 7 evaluator into the homework 5 analyzer. Okay, so these are things that the evaluator found that now the analyzer has to find. They could be found by a parser. Okay, if you compile this and run it, everything in here should be an analysis error. Okay, so, and you can get a good sense of what kind of errors to be looking for. And I gave you, I'll probably give you this with the full debugging information, though your debugging information may not look like my debugging information. The way your analyzer prints out debugging information is, to me, not that important. You could print out the debugging information the exact same way I do, or you might think of a different way to do it. So I'll probably give you this output with and without the debugging information. What's important is you have to mimic the errors. You have to get the right errors, but you don't have to get the right debugging information. So I'll probably give you this output both ways, with and without the debugging information. The debugging information may help you get a sense of how to write the analyzer. So it's a little bit of a clue of how to write the analyzer, but you don't have to mimic exactly my debugging if you don't want to. But you do have to get the exact same error messages. Okay. Okay, so this one tests a whole bunch of conditions that could have been found by a parser. And see, this tests var and set. So work on var and set. You can comment out all these others. Get var and set to catch those errors. Then get fun and lambda, like get if, while, and print to get those errors. Those are pretty easy. Get the arithmetic expressions to check those errors. Those are pretty easy. The hard ones are lambda and fun. Fun and lambda are where all the work really is. Okay, fun and lambda where the work is. Now, but these are the easy ones. These are the context-free errors, the ones that the parser can find. Then there's another file that is the context-sensitive errors, the little bit harder ones to find. See, I have too much junk in here now. Here's the errors that are more subtle. These are the errors like variable is undeclared or variable has been declared 2 times. Okay, so these are, well, if you compile this and run it. Now, these are all errors that the interpreter finds, but the way the interpreter finds them and the way the analyzer finds them now is going to be a little bit different. This one, pretty much the way the interpreter found these errors, you can copy and paste them into the analyzer. These are the easy ones. These are going to be a little bit more subtle. The way the interpreter finds them may not be exact. Sometimes it is just the same. The analyzer and the interpreter will do the same thing, but sometimes here the analyzer has to do things a little bit differently. Okay, so this one, these are a little bit harder. Okay, these are the analysis errors, and I made them separate so that you could work on these first, then work on the harder ones. Again, do the easier ones like var and set. Var and set are easier to do. Do var, set, and begin, then do the hard, then do while. That's not so hard. The hard ones, again, are going to be lambda and apply and fun. These are the hard ones. Okay. All right. So you check those, do those later. First do the context-free errors, then do the context-sensitive errors. Do the easy ones first, which are var and set, and then do the functions later. Okay. All right. So what we're going to do is I'll make this available. We spent the whole time doing this. This is a real interesting assignment. It's a real challenging assignment. It really uses everything we've talked about the whole semester. I mean, it really makes you learn how the interpreter works, because you have to mimic the interpreter in the analyzer. And actually you have to mimic the interpreter and make it a little bit different. So it's a real challenge. It's real good programming language concepts. So I'll make this available. Hopefully it'll be up there tonight, and then you have time to start thinking about it. And then on class, later in class, we can go back over this some more. Okay. So like next week, if you have time to look at this, we can we can go back through a lot of these ideas again, because this assignment's a really good assignment for the whole. It sums up pretty much everything we've done in the semester. So we'll go back through after you've seen the homework and had a chance to look at it. We'll go back and go through a lot of these ideas and talk about them, and how you would think about how you would go through and write the code yourself. So we'll go back and do these again next week, a lot of these examples. Okay, so we've run out of time. So gone over. Yeah, I hope to have this up there this evening. It's almost done. I have to, actually, what I have to do is I have to make sure I got everything described well in here. And then what I'm going to do is I'm going to take the static analyzer and strip out most of the code from it. But I want to give you some code in it. So I have to decide what to give you and what to strip out. If I strip out everything, I think it'll be a little bit too hard. So I'm going to leave, I have to decide what to leave in there and what to take out. How much am I going to write for you and how much I'm going to leave for you to write? So I have to decide on that. So I'm going to strip, right now, that's the whole analyzer. That's the completed analyzer. So I'm going to strip out some code from there. Everything else here you'll get. You'll only be writing code in the analyzer and you'll be completing it. So I'll strip out a lot of what's in there and you'll put back in what I strip out. Everything else will stay. Oh, and there's a demo version. You'll get a demo version of the program. Okay. This is a demo version, a binary demo version of the language 7 with the static analyzer. So you'll have something to test that's correct. So you'll have a working version of the analyzer in this demo folder. That's real important. You'll have a working version of the analyzer in the demo folder, and it'll come without that jar file so that you could build the jar file yourself. Okay, so this will build that jar file, but there's a working demo version of the jar file in there. Okay, all right. So going over. So we'll talk. We'll keep language. We'll keep talking. Next week, we'll probably go back through a lot of this as you've had time to look at the homework assignment, because it's going to take some real thought. It's not a simple homework assignment, real challenge. Okay. Anybody got any question about the homework assignment at this point? Anybody got a question about it? Okay. So I hope it'll be up there this evening. And I may put it up there even if it's not complete. Just, I may put it so you can start looking at it. Like if I don't think I've really written up the web page real well, maybe, I might put it up there with maybe the web page not as complete as it could be, and I'll add to the web page as I think of explanations. I'm trying to explain here the analyzer to you. So hopefully this will give you a sense of how the analyzer should work. All right. Okay. We'll quit there. Going over time. All right. And so have a nice weekend. Bye-bye.
Bye-bye. Thank you.
Bye.